Hello, my name is Pablo Vaquero, and today we'll be talking about the project about NPN transistor fabrication challenge. Okay, so in this project we are required to perform 6 different tasks. 2 of them are regarding ion implantation, p-doping and n-doping types. And then we will also be discussing certain techniques for oxidation, photolithography, metal deposition, and finally we will talk about the overall functioning of a transistor. Okay, so the first thing to talk about is ion implantation through p-doping. So the first thing to note is what is doping. Doping is basically introducing some dopants, which are other elements, into a lattice form of a certain type of atoms. We're usually discussing the silicon lattice. So by doping, we will be introducing other elements such as boron or phosphorus. And this causes the semiconductors, which in this case is silicon, to be altered and be able to conduct electricity um, in a controlled manner. So we will be the ones controlling if we want our semiconductor to conduct electricity or not. So the two types are p-type. This type basically we introduce an element that has a lower number of outer shell electrons. For instance, boron has just 3 outer shell electrons, while silicon has 4. This causes the movement of holes, and so p-type stands for positive. And then we also have the n-type. In this case, we're introducing phosphorus, which is an element that has 5 outer shell electrons, and so we are introducing a negative, more negative charge, and that's why it's n-type, or standing for negative. Then the ion implantation is basically the method to perform this doping, and it consists of accelerating these ions, either boron or phosphorus or other element in their periodic table group, by an electric field and directing this beam of ions into the surface we want to dope. So here is a sketch of what I was talking about previously. We've got as we are p-doping, we've got our boron source here. Here we have the boron electrodes. This is the analyzing magnet, and all this stands for the high voltage section. So basically, we will apply a voltage so that our boron ions can flow. Then in this area, which is named as the ion acceleration column, the ions will be subjected to an electric field that will accelerate them. And then when passing through the deflector and the electronic scanning, we will be able to redirect the flow of boron ions into our desired surface. In this case, as we want to dope the wafer surface, this is why I draw in yellow the surface of the transistor. This would be the general drawing of a transistor, and in this case, the P doped surface will be the wafer. Now we will talk about another important feature, which is the oxidation. So the first thing is why we are oxidizing our material, basically because we want to protect it and gain some important characteristics. The first of them is the excellent insulation. Basically, this eliminates any unwanted electrical current flow from our transistor. The transistor is a really small element that needs to work with a really high precision, and with this kind of insulation we ensure that characteristic. Also, we have high chemical stability. We will be performing some chemical methods, manufacturing processes, and it's important for our material to be chemically stable against corrosion or degradation, for instance. Also, it's important to withstand high temperatures, as again, some manufacturing processes will be held at high temperatures. Um, Finally, the oxidation is usually easy and uniformly grown, and oxidation can be performed either by wet oxidation, which is basically in a water atmosphere, or through dry oxidation. Okay, so now basically, here's a more detailed view of what I was explaining. I decided to choose dry oxidation. This is why I drew here the oxygen atmosphere. And basically, we have a reaction taking place, which is silicon plus oxygen to give silicon dioxide, also named as silica. It is usually performed by applying heat at a temperature of between 700 and 900 degrees Celsius. And as you can see here, we have here our silicon, and here our surface of silicon dioxide. As I told previously, we could also go for wet oxidation. In this case, instead of an oxygen atmosphere, we will have a water atmosphere, and the reaction would be really similar. We will form a layer of silica, but we will also have um, hydrogen molecules as a product. Okay, so we will be discussing now what photolithography is and how to achieve it. So basically, photolithography is a technique that enables to design some intricate circuits into the silicon wafer that we have been talking about the whole presentation. The steps are really easy. The first one is just applying a thin layer of a polymer, which is called photoresist. And then we need to expose this thin layer to some light which has a specific wavelength. So the light will pass through a pattern which is the photomask, and will create the desired pattern in our silicon wafer. So here are the two processes drawn. Firstly, we have the application of the photoresist. Basically, we have here a rotating device, um, which is our wafer, which is rotating, and then the dispense of the photoresist substance into the wafer. Then the centrifugal force will cause the wafer to expand, or the photoresist to expand uniformly through the surface of the wafer. And here's a sketch of how the result would be with the wafer, then the oxide film that we created thanks to oxidation, and finally the photoresist substance. Then we will design the desired pattern in our mask. In this case, I decided to choose just two parallel conducts, and we will apply this light, which has a certain wavelength. The the light will pass through the mask and through a series of lenses, and will impact the photoresist, which will be removed, and so our final surface will have an empty space right there. So with this drawing can be traduced into this basically. So our pattern were two parallel lines. So here we will have two parallel spots in which the photoresist was removed, and that is how we can create the pattern we like in any transistor. Now, again, we have the ion implantation, but now we are talking about the n-doping type. The explanation for what is doping is exactly the same as before, the same methodology, the same concept. However, now, instead of introducing a p-type, that is a boron, we are introducing um, a donor, which in this case I chose it to be phosphorus. So the process would be exactly the same. We will have our ion source, in this case phosphorus, would be accelerated in the high voltage sections thanks to the applied voltage. Also, it will be accelerated in the ion acceleration column and will impact our desired locations. In this case, I'm sorry, I wrote here wafer surface, but this would be the source, the drain, and the top of the gate, which can be seen here. These yellow zones which I marked are those which will be in which we will apply our N-type semiconductors. And here's a sketch of what I was explaining before. We've got our distorted silicon lattice now with a phosphorus element, and we can see how every electron is paired except for the extra electron of the phosphorus, which would be this electron right here. So this causes a negative charge and will allow the flow of electrons. Now we talk about metal deposition. Basically, in metal deposition, what we are interested is to create some contacts for the source, the drain, and the region on top of the gate. Those regions which were doped with phosphorus. So the first step, and it's the step I will be explaining after, is the PVD, also known as physical vapor deposition. This basically introduces a thin layer of our metal into our desired desired parts. Then we will have the pattern through photolithography. As we just explained before, we can design the pattern we want to perform. And then the third step is etching. Etching can be either wet or dry, and it's basically its function is to remove those excess areas containing metal and leaving the pattern we designed through PVD and patterning with photolithography. Okay, so now the main technique to deposit that metal is PVD. So basically here we have an atmosphere in vacuum, and we have our metal here. It can be, for instance, titanium. So a high velocity jet will impact the metal, and the metal will be directed at high velocities in this direction. Here is our component, or our part we want to fill with metal, and the metal, as it is molten and it is traveling at really high speeds, will be deposited in the surface of our component. Okay, so now here's a more detailed view of how a transistor is. We've got here our wafer, which was doped with a p-type. We have here the source and the drain. Here I forgot to write the D standing for drain. And here is the gate. The gate, as we had previously said, is protected by the silicon oxide, which is here, and the upper part would be the photoresist. This photoresist will have the pattern designed through the photolithography, as well as the source and the drain, which will be covered by the deposited metal. So initially, basically, we have the PD doped and N doped regions, and we have here this area separating them, which is called the depletion area. That area basically acts as a barrier between the both types of semiconductors. So the basic idea here is that when there is no voltage in the gate, there is no flow of electrons between the p p-type and n-type because the depletion region acts as a barrier. However, when we turn the gate on, or when we apply a voltage to the gate, um, the start of electrons, there will be an applied voltage, and this applied voltage will be transferred to the n-doped and p-doped regions, and there will start a flow of electrons. See that the electrons flow from the n-type to the p-type, and the direction is opposite to the direction of the current. Why is this important? This is important because thanks to the doping of the silicon, either with donors or with acceptors, we have been able to create a device that functions or transmits electricity the way we want and whenever we want. And that is why transistors are currently one of the most important electric devices in the industry, because they allow the desired flow of electricity with our desired patterns that we have designed with photolithography and metal deposition. So thank you very much for your attention, and I hope you enjoyed.